Welcome. Today we will explore database recovery techniques. These techniques are crucial for ensuring database consistency after system failures. Let's dive in and see how databases maintain their integrity, even when things go wrong. Database recovery is essential because several challenges can compromise data integrity. System crashes can occur during transaction processing, potentially leaving the database in an inconsistent state. Power outages can disrupt operations and affect data integrity. Hardware failures, such as disk crashes, can lead to significant data loss. Therefore, database recovery mechanisms are needed to maintain the essential asset properties, atomicity, consistency, isolation, and durability after failures and to ensure a consistent database state despite these challenges. There are several types of database failures that can occur. Firstly, transaction failures are individual transaction errors that don't affect the entire system. This can include logical errors in the transaction code, constraint violations such as a unique key violation, deadlocks between transactions, or user-initiated aborts. Next, system crashes refers to an unexpected termination of database operations. The reasons can include power outages affecting servers, operating system failures, or database software crashes. Media failures refer to physical damage to storage devices, such as disk head crashes or physical damage to storage media, resulting in the loss of data on the affected devices. Finally, network failures are communication issues that arise in distributed databases. Examples include network partitioning, message loss during transmission, timeouts during distributed transactions, and node isolation in cluster environments. Transaction logging is a mechanism that records all database modifications to maintain recoverability. This involves recording all changes before they are applied to the database, providing a chronological history of all transactions, and enabling undo and redo operations. It is a critical component for ensuring asset properties. Transaction logs are stored in separate physical storage from the main data files to ensure that log data is available, even if the primary storage fails. As you can see, the transaction manager sends operations to the database. The transaction manager also communicates with the log manager. The log manager then writes it to the transaction log. There are various types of log records used in database recovery. Update log records track changes to database items during transactions. It contains the transaction identification, data item identification, the old value or before image, and the new value or after image. These records are used for both undo and redo operations. Transaction status records mark transaction boundaries and status changes, including start, commit, abort, and END records. These are essential for determining transaction state during recovery. Checkpoint records provide periodic snapshots of active transactions, listing active transactions and buffer contents. They limit the recovery scope to reduce recovery time. For example, a transaction start record might look like this. Start with the transaction ID equal to T1 and the timestamp included. Update records show the old and new values. A commit record marks when the transaction is complete, and a checkpoint record keeps track of active transactions. Write-ahead logging is a fundamental principle ensuring recoverability in database systems. The WAL protocol dictates that log records must be written to stable storage before data changes are made. A transaction cannot commit until all its log records are safely on disk. This ensures that changes can be redone or undone after a crash, providing durability and atomicity guarantees. WAL is widely used in most modern database systems. First, a transaction starts, then the log is written, then the data is written, and finally it is flushed to disk. Keep in mind the WAL rule that logs must be written before the data. Database recovery often involves two main processes: undo and redo recovery. Undo recovery reverses the effects of incomplete or aborted transactions. It uses before images from the log records and is applied to transactions that were active but not committed at the time of a crash. This process restores the database to a state where only committed transactions are reflected. Redo recovery, on the other hand, reapplies the effects of committed transactions that might not have been fully written to disk. It uses after images from the log records and is applied to committed transactions whose changes might not have reached the disk. This ensures the durability of committed transactions. Checkpointing is a technique used to limit the amount of log processing required during recovery. It involves periodically writing all modified buffer pages to disk and recording a checkpoint entry in the log. This reduces recovery time after a system failure and allows log truncation to save storage space. As time progresses from left to right, we see various transactions occur, a checkpoint which indicates a point at which the database state is consistent, and then a system crash. The algorithms for recovery and isolation exploiting semantics, or ARIES, recovery algorithm is a sophisticated method for database recovery. The ARIES recovery process includes 3 phases. First, the analysis phase scans the log forward from the last checkpoint, identifying active transactions at the crash time and determining dirty pages that might need redo. Second, the redo phase starts from an appropriate log record and reapplies all updates, even for aborted transactions, bringing the database to its exact state at the time of the crash. Finally, the undo phase rolls back all active transactions at the time of the crash, processing transactions in reverse order and writing compensation log records. Key features include write-ahead logging, where log records are written before data pages are modified. Repeating history during redo by repeating all actions since the last checkpoint. Logging changes during UNDO, writing compensation log records, page-oriented redo, fuzzy checkpointing where there is no need to flush all dirty pages at checkpoint, and nested top actions, which supports complex operations. In summary, database recovery ensures data consistency after system failures, with write-ahead logging being fundamental to most recovery mechanisms. Undo and redo operations restore the database to a consistent state. Checkpointing reduces recovery time and log storage requirements. ARIES combines these techniques into a comprehensive recovery method. Recovery techniques are implemented in various database systems such as PostgreSQL, Oracle, SQL Server, and MongoDB. Thank you for watching. Any questions? If you like this video, hit that like button and don't forget to subscribe. Visit codelucky.com for more such useful content.